Have Steve come up and talk about some new stuff that's going on with the speaker team.
So next week, I'm going to do my outside stint head amplifier presentation, so we're going to do that first. It's going to be $10 per kit, so if you're interested after the presentation next week on Tuesday, just let me know when you sign up and move forward with that. But first I want to show you a demonstration of the speakers that I'm building for, this is going to be later in the semester. The goal is to get a complete system for $50 or under. Right now what I'm looking at is these two drivers are $9 a piece. So that leaves, after materials for the cabinets, about $20 for the amplifier, which is pretty tricky to do. So an alternative I thought of, I found this one on Online Parts Express. It's a 20-watt amplifier, about 20 bucks. I haven't listened to it yet, so I'm not sure if it sounds good or not, but one option is that we could focus on doing the speaker design this semester and then just simply buy an amplifier to power the speakers. So we'd have the headphone amplifier would be sort of the electronics, the headphone, or the amplifier building lab, and then the speaker lab would be more based on acoustics, so building these speakers. So what I have right now, this is a 120 watt per channel amplifier, so it's left, right, and so that was designed and built in less than 24 hours. It was myself, Eric Tarkelson, Brandon Boozer, the former president, and it was the day before design day we needed an amplifier, and I've got the schematics right there if anybody wants to take a look at them afterwards. But it's actually, it's really overkill for these speakers because these are limited at about 20 watts per channel. And so it's a 120 watt amplifier per channel. So it'll tell you when you're trying to push it too far. What actually happens is you're limited by the excursion of the speaker. So if it tries to move too far out, then it'll just basically clip and you'll hear it kind of like cracking. Not sure how loud I want to push it today, but if I do push it that loud, you'll hear it start to crack. And that's your kind of indication to turn it down. But if I could make better, more powerful speakers, the amplifier could power them. So I could technically take 6 of these and stack them on top of each other and still power with this amplifier and have a little bit of power to spare. But kind of the tricky thing is trying to take this and, number one, shrink it down into the size of an outside tin, but then number two, try to make it battery powered. So it has to be very efficient, and you have to have a fair amount of battery capacity. So that's still kind of a challenge I'm working on. Hopefully I'll get it eventually, but I find you need at least a couple watts, and my original design was 0.5 watts per channel, which wasn't quite enough. But as you'll see, 20 watts per channel is plenty. The subwoofer, well actually everything you see here was designed and built by AEE minus the MP3 player. So, but we're working on it. Next semester. So the subwoofer I think was maybe 2 or 3 semesters ago. We started with just a bare driver and then we designed the entire cabinet around it. The reason I had that hooked up, these will do up to 20 kilohertz and then down to 80 hertz. And the way they're designed with a sealed enclosure, 80 hertz is the cutoff frequency, so it rolls off. It's basically a second order filter, so it rolls off at 40 dB per decade. And then the crossover filter I had built in here for the subwoofer starts rolling up. So it's basically a filter that starts at 80 hertz. So this will handle 20 kilohertz to 80 hertz. And then this will do your 80 hertz to 20 hertz. So what I'll do first is play it with everything hooked up so you get the full range of frequencies. But then I'm actually going to unplug the subwoofer to kind of show you how much these can produce without a sub. Because if you're talking about portable, you're not going to want to carry one of these things around. So I've got 3 songs I'm going to play for you today. One's kind of acoustic. It doesn't really rely on bass. And then there's another one, it's called Such Great Heights by the Postal Service. It's the one where it's got like the different beeps, so it kind of shows you the channel separation and neat stuff like that. And then there's another one, it's something by the Basstronics, or they use it all the time on YouTube for subwoofer demos. So what it has this really low frequency content encoded in it, so you can actually see the driver moving. So it's maybe like 5 or 6 hertz or something. You're not going to produce any sound, but it's kind of neat to show you how much the cone actually moves. A little bit of a buzz in this one. Push it pretty hard to hear that, so I don't want to kill your hearing. But the point is, 20 watts is a heck of a lot. So remember, it's 20 watts average, not 20 watts peak. So most of the time when they say it's a 100-watt amplifier, they're talking about peak power. The average is always much less. So for a normal situation like this, 20 watts is definitely plenty. Okay, so next demo, I'm going to unplug the subwoofer. In case you don't believe me, here are the wires. So, no sub. What do you think? Woo! Most of it's still there. That's Eric something or other. I think so. Yeah. All right. So next demo. Should I plug this up back in or? Yes. The buzzing you're hearing, that's coming from just the speaker, so it's something in the amplifier that's still to be fixed.
So what's the lowest frequency that can handle?
To do low frequencies in an amplifier is pretty easy, but to do it acoustically is much more difficult. I think this amplifier can go down to DC. So, I mean, if you think 2 hertz, 1 hertz, and then DC is 0 hertz. So, the driver in there, I think it can go down to, it's flat to about 33 hertz, and then below that it starts to roll off a little bit. The lowest you can practically go, at least maybe 25 hertz. I mean, it's still going to roll off a little bit after that, but you can equalize it to get it relatively flat down to 20 hertz. Here's the bass demo where you'll see the driver actually physically moving. so that's, any questions? Nothing? Werner?
When can you build these?
Yeah.
I'm sure we'd all like to know.
Yeah, I'm shooting by the end of the semester, but if you order them in quantity, the drivers are $9 a piece. If you get them one at a time, they're $12.50 a piece.
Do you have the cabinet geometry already kind of optimized, or?
Yeah. So the big thing for a subwoofer, the reason you make a certain cabinet geometry over another one is resonance frequencies. So for a subwoofer, the frequencies are so low, you're talking about wavelengths that are like this. So in a subwoofer, you can make it just a cube, no problem. When you talk about a full range speaker like this, 80 hertz to 20 kilohertz, your wavelength in air starts getting really small, so the dimensions start to matter. So the reason, anybody know why it's this shape, why it's not a box or a cube?
Is this a quiz from your phone?
Oh, I think I did explain it, yeah, I don't know. So the answer is, if you have a box like this, all the dimensions are the same, right? So you have from the top to the bottom, from the left to the right, and then the front to the back. That spacing is exactly the same, right? So if you're talking about resonance, you're going to get these modes setting up, and they're all going to be the same. So you have three basically adding to each other. And if you have three things resonating at the same frequency, it just takes off, and you don't want that. So what this does is it's spaced, the dimensions are, I think, for example, this is 1 unit, this is 1.6, and then this is, I think it's 2.1 or something. It's the golden ratio. So the idea is you space them out equally so that none of them overlap. Because when you're setting up when you're trying to calculate your resonance frequencies, you'll have, I don't know, say one at 100 hertz, for example, and then you'll have one at 200 hertz and 300 hertz and 400 hertz. And so you basically get all these harmonics, is what they call them. And if any of them overlap, then you get the possibility for it to start resonating. And does everybody know what I mean when I say resonance? Have you heard somebody's got a big subwoofer in their trunk and you can hear the trunk just rattling? Yeah, that's the trunk is actually resonating with the speakers. So resonance in a speaker cabinet is when the cabinet itself actually starts moving like that. And the reason you wouldn't want that is the speaker's putting out a certain amount of frequencies, and if your cabinet is also putting out sound, then it's not the original sound that you intended. So you want to try and minimize that as much as you can.
How long of a project do you think this
The speakers,
for everything? You
everything.
want to do,
The Altoids tin, we did it in 2 weeks last time, 2 3-hour labs. But I think if we did a 4 or 5 hour lab, we could probably get it done in one session. The speakers, what we're probably going to do is pre-cut all the panels. So it'll just be a matter of gluing and clamping everything together, and then just a little bit of wiring. There's 2 terminals on the speaker that you have to solder, and that goes to the connection on the back there. So the speakers themselves should be really quick.
So this is the base of the banner, so can I make that subwoofer smaller or man?
You could. So it's basically in all of engineering, you're dealing with design trade-offs. So the reason the subwoofer is so big is because basically you can't buy one like that because nobody would buy a subwoofer that big. So I mean, obviously they want to make subwoofers as small as possible, but that affects the frequency response. So if you want an ideal flat frequency response, this is what you need. What they end up doing in practice is they make it a little smaller and you get a little bump in the frequency, and then they can just equalize that out with filters. But if you want a pure flat response with no filtering, then this is kind of the size you need.
So like if you want like hetero and with what's it called, hetero frequencies,
Mhm.
so within the base it's like a distal, whereas having it be more flat there, or really?
Well, what I have right now is, kind of drive up here. So there's frequency and then amplitude. So right now these 2 speakers are kind of designed to do this, and then the subwoofer, this is pretty much going to go like this. So can't go negative, but. So the idea is that they're crossing over right at 80 hertz, and then if you add these two together, you should get a flat line. So you should, that's the idea. But it's another thing to measure and actually see a flat line. But what I was thinking of doing, I have a sound pressure level meter, but I'm not sure how low that can go in frequency. So I could just sit there and measure the decibels and hook it up to an oscillator and just vary the frequency and see what the reading is. But that's
I've got some like stand-up speakers for like home stereo, and they have a hole at the bottom. Now, why would they do that instead of?
so these, every speaker you see up here, the sub and then the left and the right, they are what they call sealed enclosures. So it's completely 360 degrees sealed. What that means is you basically have a certain volume of air in there, and if you think the speaker works by the cone moving back and forward, right? It pushes air in, pushes it out. So it's got this volume of air in there, and when it moves out, you're basically trying to expand that volume, right? So it doesn't want to expand, right? It's going to kind of resist that. And then when it goes in, it's going to try and kind of suck it back in, right? So it kind of acts as like they call it a restoring force. So it damps the motion of your driver. The reason I did these as a sealed is the response, this kind of curve right here is second order. So it's really easy to make a second order filter for the bass to try and compensate for that. When you're talking about that little vent, they call it a ported enclosure. So this is sealed, that's ported enclosure. The reason they do that is you can get a little bit lower frequency response, but kind of the drawback is, you know, time domain and frequency domain, right?
Say that again.
Do you know time domain and frequency domain?
Not entirely.
So there's frequency like 20 hertz and 20 kilohertz, and then there's time domain, basically how it performs in time. So if you do a second order filter, it doesn't roll off as fast in frequency, but in time.
So benefit versus, you know.
Well, the biggest thing, you can put it in a smaller enclosure. So the drawback, though, it affects the frequency response.
Okay.
So if you're trying to predict exactly what frequency response you're going to get, a sealed is best.
Okay.
But with a ported, you have a whole bunch of different factors. You have not only the cabinet volume, but then you have the length of the port, the spacing of the diameter of the port, where it's positioned on the front or the back.
Okay.
There's just a lot more variables that go into designing a speaker when you're doing ported enclosure.
Okay.
But technically, you could get a better frequency response if you kept it at everything, right?
So what you're going to get is it's going to be a second order response. So it's going to kind of go like this. Ported, which is a fourth order response, it'll kind of go like that. It'll get you a little bit more of that bass extension, but the drawback is that the time response is not as good.